Professor Anupam Joshi will be giving a talk today on AI for cybersecurity. Anupam Joshi is the Oris Family Professor and Chair of the Computer Science and Electrical Engineering Department at the University of Maryland, Baltimore County. He is the Director of UMBC's Center for Cybersecurity. He's a Fellow of the IEEE. Dr. Joshi obtained a Bachelor of Technology degree from IIT Delphi in 1989 and a master's and PhD from Purdue University in 1991 and 1993, respectively. His interests in research are in the broad area of network computing and intelligent systems, and his primary focus has been on data management and security, privacy, in mobile and pervasive computing environments. He's also interested in policy-driven approaches to security and privacy. Dr. Joshi has interest in semantic web and data, text, and web analytics, especially their applications to cybersecurity and healthcare. He has published over 275 technical papers with an H-index of 87 and over 2,800 citations for his work. He's been granted 9 patents and has obtained research support from the National Science Foundation, from NASA, the Defense Advanced Research Project Agency, the U.S. Department of Defense, NIST, IBM, Microsoft, Qualcomm, Northrop Grumman, and Lockheed Martin, amongst others. It gives me great pleasure to introduce our next speaker for the evening, Professor Anupam Joshi.
Thank you. I appreciate the kind words of welcome, and I truly appreciate the Baltimore chapter for inviting me to give a talk today. I will confess by stating that following giants of the field like Kleinrock and Schulzrien and Steve Bellowin and others, it's a hard task, but I will try. A couple of ACM plugs, if you would. So we are organizing, I'm the general chair of ACM's CodaSpy, which is the big conference on data security and privacy. And the 12th iteration of the conference is happening next week, right here in the Arundel Mills area. So if you haven't registered yet and would like to come, please go to codaspy.org. There is also an option this time. We're running the conference in a hybrid mode, so there is an option to be remote and attend the conference. A great set of talks, wonderful invited speakers. So I hope you'll consider it's an ACM activity and it's in the area. Also, a plug for CACM. You know, there was a slide earlier, so I'm the one of the editors on the Viewpoint side. So if you have clever ideas about security and how to make things better, that's a good venue to consider in addition to any journals and conferences. So we heard from Professor Bellowin a very nice history of how the internet and its security evolved. I will be looking to the future on saying, you know, some of the challenges that Professor Bellowin had begun to identify in his last few slides about the future, about sort of state actors and adversaries. How do we defend against those kinds of actors? And the claim that we've been making, we've done some work in this space for the last few years with interesting results, is that AI can help. But a stronger claim I want to just make in the beginning, happy to discuss with you, with others offline, is that you actually need foundational research in AI to make that happen. It's not, I mean, a lot of the current work is just, let's take, you know, whatever is the current best deep learning method and throw it at this problem. But we need more. Anyways, I'll say some more about that. So if you look at the kind of the sophisticated actors that Professor Bellowin was describing at the end, right? Or if you are dealing with internal threats, whether by acts of omission or commission, there is a gap between what we do today, and I'll say a little bit more about that later, and what really needs to be done at scale to counter those kinds of adversaries. And as we begin, and again, it's a point identified by Professor Bellowin earlier, as we begin to move to cyber physical systems, right? Systems that combine the information world with real physical effects, I think these challenges grow. And you heard about Stuxnet. Professor Bellowin suggested attributions. Living in this area, I will be very careful not to suggest attributions on who may or may not have developed that system. But it combined some of the things that he was talking about: reconnaissance, monitoring, figuring out the behavior. The vector was a laptop of an employee who used to take the laptop between their home and the office, from what we understand. And a very deep understanding, not just of the penetration method, but of the Siemens PLC that controlled those centrifuges, how those centrifuges were monitored, because believe it or not, there are people who are actually monitoring how those centrifuges were operating, and exactly what you needed to do in terms of accelerating and deaccelerating the spin to cause them to physically fail. So there was a cyber attack which was informed by the physics of the centrifuges and which actively subverted the monitoring system. So allegedly, the people who were monitoring it didn't see that something strange was happening, because otherwise, if the centrifuges were speeding up and slowing down, the engineer monitoring them would have shut them down. That's not supposed to happen. So the claim I'm making is that to sort of address these kinds of challenges, you need fundamental research in AI, foundational work. And I will talk about some of the work that we have begun to do in this space. I do want to give a shout out in the audience. I mean, from UMBC, we have a ton of alums at APL. In fact, we very proudly claim that Dr. Ralph Semmel is an alum of our department, but there are a lot of alums, some of the names I see on the screen. So, thank you for coming, and thank you for APL for being such a good partner to UMBC. So I'm going to talk a little bit just on traditional, not so much on cyber physical for a minute, but just defending traditional computer systems with information that an adversary might want. And if you look at what happens today, right? The APT kind of attacks, as you heard from Professor Bellowin, unfold over a temporal scale, right? This is not a DDoS attack that someone is trying to bring you down. It's very easy to detect when you're being attacked using DDoS, right? These are sophisticated actors that are slowly pushing the boundaries here or there. So you have this attack unfolding over a temporal period, and it's typically not an attack on a single component of your system. It's not your firewall that's being hit, and that's all you need to. Maybe something was done to your firewall. Maybe one of the accounts was taken over. Maybe some file was changed, and this is all happening in a distributed manner. So geographically and spatially and temporally sort of separate. And what you want right now, what is sort of the state of the art, is you rely on Superwoman, right? So there is a person, watch standing, seeing whatever SIEM system you have, looking at various events that are happening, and in their head saying, aha, this thing happened 7 days ago. I read an article 3 days ago that said that people were beginning to exploit this kind of a vulnerability. I know that I have that kind of software installed in my system. I suddenly noticed that that process is running and touching files that it doesn't normally touch. And I noticed that a network connection has been opened to a server that this system has never previously. All of these are relatively innocent things by themselves, but having a smart analyst, a superwoman, if you would put them together, is what the state of the art is. And this is simply not scalable, right? Because maybe if you are APL, you can afford to have a few of these really, really smart people defending your networks. At UMBC, we have one full-time staff member and students, right? Graduate and undergraduate students that are our network defense. And we are representative of most of the real world. So to the extent that AI can step in and augment the human resources, right? With humans both in the detection loop and on the detection loop, or actually I would rather say the detection and response loop than what it is. So here's a simple example, right? Which current systems find hard to understand. So this is Petya, which was 2016, and on the right-hand side, you have NotPetya, which was 2017. And it's doing the same thing, except the attack vector changed. And that is sufficient to defeat most modern systems, right? But as a human being, even minimally trained in cybersecurity, looking at this, I would say, yep, this is the same thing, right? This is an attack. This is a ransomware attack. Okay, so as I was mentioning to you, this is a particular APT Reaper, and you will notice that there's sort of a 2-year, almost 3-year time span, right, over which multiple CVEs are being deployed. I'll say a little bit more about this, right? In this slide, and this is thanks to our friends at MITRE, and this is a pretty old slide now, right? But my understanding is that some of the elements are still classified. So A, I don't know what they are, and B, even if I did, I wouldn't be able to tell you. But the key take-home message, and what you see at the bottom for those of you who are, and I can't do a laser pointer, right? Because most of this, a lot of this is remote. So at the bottom, what you are seeing is what is called the cyber kill chain, which itself has origins in the US Air Force kill chain. Don't want to go into details there. But the idea is that this is a sophisticated adversary. Sort of the rough version of the story is the following. A large defense contractor, not APL, their missile kind of systems people, 5 extremely prominent scientists working there got an email from the American Institute of Aeronautics and Astronautics, or at least what looked to be from that institute, saying that they had been nominated for the Outstanding Scientist of the Year or something like that award. And there was a PDF nomination form that they had to put some details in and send back, right? You heard Professor Bellawin talk about how these sophisticated adversaries do this. I can give you lots of other examples. Around the time of the Fukushima earthquake, right? Excel spreadsheets went to people in Japan that had a malware embedded, saying radiation measurements around Fukushima. This was to the scientists who were involved in the cleanup effort. Around the same time, the same malware was embedded in a PDF document that purported to be an appeal from the Tibetan government in exile to Tibetans worldwide, saying, let's sign this petition, saying Tibetan people should be sort of given their freedoms and things of that nature, right? So you can speculate who might be the adversary behind such an attack. But fairly sophisticated targeting, and in this case, the only reason it got detected was the fact that these were 5 really smart people. They talked to each other. Hey, did you know I've just been nominated? Oh, so have I. And they were like, really? All 5 of us working in the same unit have been nominated as the outstanding scientist by the same organization? They went to the security people. The security people set them up on a honeypot, had them open the email, and they tracked an adversary for 2 years. And the row you see in the middle, the CVEs, there were 40 such, these are all 0 days. The CVE numbers were given later. The adversary over a roughly 2-year period had 40 new 0 days that they used, because every state level, every good actor knows that just because they're in your system, it doesn't mean that the attack they used wouldn't be shut down 6 months later. So they were constantly keeping themselves fresh. And the implants they used to exfil, I believe, are still classified. So this is what you're trying to deal with And unless, as I sort of go back to the previous slide, right, unless you have this superwoman sitting in your threat intelligence SOC, you're not going to detect these kinds of things. So this is a game I like. The original inspiration for this were some slides from Gary Gagnon, which is about hockey, and that's not a game. Well, I grew up in India. When you say hockey to me, it means field hockey, but in the American context, it's hockey played on ice. The original slides were about that, but if you don't understand cricket or hockey, think of, again, I was about to say football, think of soccer, right? The goalkeeper doesn't turn and face the goal, look at the goal line, and swat away the soccer balls as they are about to cross the goal line, right? The goalkeeper looks outside. The goalie says, okay, what is the offense doing, right? Did their midfielder start running up? Did the left field, winger cross to the center, right? Where is the ball moving? Because you are constantly calculating what the attack vector might be, and you are sort of proactively, predictively trying to defend against that. You're not waiting till the ball has been kicked at the goal. That is simply too late. Right? Unfortunately, most of our cyber defense happens after the traffic comes into our firewall. Just, every major organization today has a threat hunting team. Why do they have a threat hunting team? Because the assumption is our defenses are not perfect, someone would have gotten through, right? So certainly, I'm not saying you wouldn't need threat hunting teams, but the idea is that hopefully with some AI, you can begin to sort of be more outward looking, be more predictive on the kind of things that may be coming down the pike and start to defend against them, right? So a good player sees the game as it evolves. And it's not just their own actions, but the actions that other people may or may not be taking. So what we've been trying to build over the last few years is a system that absorbs sensor data from the kind of places that you would expect to see, right? So these are your network sensors and firewalls and host sensors and whatnot. But we also look around at web forums, chat rooms, discussions, tweets, and we have tried, it's hard, dark web, right? To see what are people talking about in terms of potential future attacks, right? And brought to bear techniques. So if you would, we ingest knowledge from those sources as well as the traditional sensors, and then try to reason over them, much like an analyst would, to see if we can detect an attack. And in the process, we use this ontology called the Unified Cybersecurity Ontology. I will not get into the details of that. If any of you here are AI, semantic web, knowledge representation kind of aficionados, I'm happy to talk to you about this. Short version, we can express most of the things that something like STIX or ATT&CK can, but we can do it in a richer framework that is more amenable to first order logic and that kind of formal reasoning methods. So, in our current iteration, we can do what STIX 2.0 did. I know STIX has been evolving and doing new things, but the idea is that we can capture some of these higher level concepts like what is an attack? An attack is launched by an attacker. An attack may be part of a campaign. Every attack uses certain tools, sort of technologies and practices. An attack is visible because of certain kind of indicators. An attack may have a mitigation, etc. So we can capture these and not just capture and display them a la STIX or attack, but we can then feed them into a reasoner, into an AI system that can think about it and say, hey, I think this is happening, and I think this is how you should be reacting. So essentially, we detect potential new vulnerabilities from these sources that I talked to you about. From the data we are seeing from the sensors, we recognize the context of the systems and the potential attacks and intrusions that may be happening, and then we reason over them to identify actual attacks. And the one thing that we focused most of our initial attention on was deductive reasoning. So here's an example of the kind of deductive process you might do. You might say, okay, look, most analysts have certain background knowledge. I'm just going to capture it and represent that in my ontological framework, right? So there are new vulnerabilities that someone has discovered in a software, or basic facts like, household machines have DHCP addresses that are often compromised and used as zombies. Because they are DHCP addresses in household machines, say in Verizon's DHCP range, they are unlikely to be a server that someone would want to connect to. Then there is the observed state of the system. You can capture things like what software is installed, what versions, what processes are running, how much memory are they consuming, how many page faults are they causing, what files are they touching, how much traffic is being generated, what is the TTL of the packets. I mean, all kinds of indicators can be captured. You can also capture in this kind of a framework organizational policies, right? People in the asymmetric information systems group never interact with the outside travel agency, right? Believe it or not, one of the things that I'm pretty sure was an attack, I just discarded that email, was something that came to me allegedly, from our travel agency saying, you're for this such and such conference, here are the proposed bookings and things of that nature. Since I don't use that agency, I pretty much was sure that I should not be opening that proposed itinerary, right? But again, organizations often have policies about what communication is allowed, and you can capture those policies in this kind of an ontological framework, and then you can write rules deductive rules that say, if an email from a travel agency with an attachment went to a person in the group X, and a process is running with the PID of this person that has known vulnerabilities that your scan of the dark web told you about, and it is making connections to previously unvisited hosts in the DHCP range of etc. I mean, again, this is not perfect knowledge. This is not guaranteed attack, but this is the kind of thing that an analyst would think about and say, something may be happening here, let me look. And this is the kind of thing that a machine that is reasoning can do much faster and alert analysts where they see things. So this is deduction, right? But then you can do more once you have things in this kind of a framework. And our research in this area is, so in that, we have several papers and even in some cases prototype systems that we can show. But here is where you can go with something like this. So that is deduction. But for those of you who still remember your logic course from college, you can also do induction or abduction. So let me give you an example of abduction, right? So let's say you knew that Chrome version whatever, right, has a certain vulnerability that manifests itself in certain way when a site is visited in a certain domain. You notice that something similar is happening, but you're not using Chrome, you are using Microsoft Edge. Now, in this case, actually, the abduction is relatively straightforward because Edge is also built on Chromium, right? So let me make the example harder. What if you're using Mozilla Firefox, right? Well, that's not built on the same code base, but you can abduct, you can propose as a hypothesis that, well, perhaps Mozilla suffers from the same vulnerability. That's why I'm seeing this flaky behavior, right? Which is reported in Chrome, but hasn't been reported in Mozilla. So I don't have a deductive rule saying an attack is happening, but I can abduce that an attack may be happening. So it's basically saying in my graph, right? If you don't want to think of this as a reasoning, and if you want to think of this as subgraph isomorphism, which yes is very, very hard to do in the general case, right? But what you're saying is that my subgraph is just missing an edge. Otherwise, it would have matched the graph exactly. So you can begin to do these kinds of things once the framework that we have created is in place and is actually ingesting all this data. So again, this is the kind of thing, research where you have to push the state of the art. Let me give you another example where you have to push the state of the art. So most of even the deductive reasoning today in formal systems in AI is not probabilistic, right? You essentially say, if A, B, C, then D. But really, for something like this to work at scale, you want to be able to say, well, I sort of have evidence of A, 90% certainty. I sort of have evidence of B, 85% certainty. I sort of kind of have evidence of C, 60% certainty. What's the probability that the consequent is also true? So probabilistic reasoning has been a known problem in AI for a very long time. It's just very, very hard to do at scale. So those of you who've played around with Markovian logics and things, I mean, you know how hard it is to do. So you need fundamental research, and I think this is a good motivating problem where there's a lot of ROI if you're able to crack those kinds of problems. So we built a prototype system. This was some work in collaboration with IBM Research, where they provided us significant funding, and we sort of collaborated with them, which kind of did this kind of thing, and actually worked on the ransomware example that Professor Bellowin was earlier talking about, right? So we know from reading about ransomware in textual sources that ransomware will typically download and upload software keys from external servers, and then it will try to modify sensitive files. And one of the first things most ransomwares do is to modify your master boot record. Right? These are facts we know because we have read this information automatically and ingested it, right? Then we can read reports saying, hey, there is a new ransomware called WannaCry that uses malformed SMB, so the eternal blue vulnerability, to gain access to a victim. We can be, so those are things that you have already asserted in your knowledge graph. Your reasoner knows about it. Now you are dynamically asserting facts into your knowledge graph from the ingested network and host data. I noticed that, Snort tells me that I'm seeing malformed SMB packets, right? My Wireshark or whatever tells me that I'm seeing downloads from an IP address that I've never connected to before. I noticed that some files that are never touched are beginning to be modified. HostMonitor tells me that, Procmon tells me that. And then you essentially do this reasoning saying, in light of what I read and what I know, this is probably WannaCry. And then, and this is research that, so this is the part of the work we've mostly done, and the part that we are pushing forward is, and then we want to say, and what you should do while you alert the human, right? What you should do immediately is this. And we built a prototype, so you can see that, we're using, the attacker is doing an Nmap scan and then is sort of using the SMB vulnerability. And our monitor is, Snort agent is telling it that, hey, it sees Portsnet scanning, it sees bad SMB traffic, it shows some downloads that it doesn't recognize. The file monitor now says, hey, there are some new files being created, and files that you have deemed as sensitive are being modified. The process monitor, typically, if someone begins to encrypt your files, your processor utilization will shoot up. So your process monitor could say, hey, processor utilization is shooting up, and effectively your system can now deduce that an attack is happening, right? Even though these are events that are temporarily and sort of potentially spatially separated happening on different machines, and we built a prototype system that could sort of detect this kind of an attack and also show you why it thought an attack was happening. And that's the other advantage of these kinds of systems. You could query the system and say, why did you come to this conclusion? And it can show you the proof chain it built, in effect, to say why. So that's sort of the overall picture. I do want to spend a little bit of time getting into some more technical details on the on the knowledge extraction part of it, right? So we want to be able to read text and find entities and their properties and their relations and the events that they are a part of, represent this in some general knowledge base with provenance and probabilities, even though we can't use probabilities right now. We want to be able to do, and I know there is a lot of people at APL that do this kind of work, just not in this domain, right? So you want to be able to do what is called entity co-reference resolution. You want to be able to say, the Anupam being referred to here is the same as the Professor Joshi being referred to there, right? So you want to be able to say they are the same things. And then we want to be able to link these to external background knowledge bases, right? So for example, a cursory thing in Wikipedia will tell me that Kaspersky is, a Russian firm. And that may or may not be relevant to my defense posture, right? I mean, these days it is, but those are facts that I can ingest directly from Wikipedia, and Wikipedia very kindly makes it available in a format called Wikidata that we can just pull in. So, you want to be able to read text like this. I won't read the text, but it's describing a vulnerability. And you want to be able to then take the background knowledge that a human analyst has and construct a knowledge graph, right? In our UCO ontology. And I don't want to read this graph to you, but Flash was something that Professor Ballawin mentioned. So this is basically saying that, I don't know, the Chrome, Safari, and Edge are all browsers. So you can guess that this slide is about 2 years old now. And they all have this thing called the Adobe Flash Player. It also tells you that Safari is owned by Apple and Microsoft owns Edge. Should be an animation here. Right. So the blue edges are giving me what is called a users relationship. Safari uses Adobe Flash Player. Google Chrome uses Adobe Flash Player, right? The Adobe Flash Player uses the SpiderMonkey engine, which in turn uses an iframe to do something. There is something called the United Hacker Group, which has an attack called Replayer, which does this iframe business. So then you can see some relations that talk about how to mitigate an attack, right? So the attack is remote JavaScript execution. The SpiderMonkey engine causes that, but it can be mitigated by something called the Replayer blocker. The red link is an edge in the knowledge graph that says SpiderMonkey engine has vulnerability remote JavaScript execution. So what you want to do is to read text like this, and you can see the symbol of our friends who funded some of this research also in the neighborhood. I know you guys work with them too. You want to read something like this. These are examples of text they gave us. So, and these are not super secret. These are like after action reports, about 1.6 terabytes worth of after action, publicly available after action reports that say what an organization found out post facto about the malware, right? The idea is if we can perfect the techniques here, then we can be forward looking to see what is being discussed in blogs and forums and things like that. But you want to be able to see things like there is a group called Nikon. It uses spearphish documents with a certain vulnerability. There is a trick here though, right? Should the Nikon group be associated with suspicious email? Because there's sort of a lot of text separating that. And those are the kinds of sort of real research problems that you have to deal with, right? So we built a pipeline to take this kind of data, right? And to first do NER, so the named entity recognition. Nikon is a name, Microsoft is a name, Adobe is a name, Flash Player is a name, JavaScript is a name, etc. And then we built systems where you would do relationship extraction. This software has vulnerability, this vulnerability, right? This group uses this exploit, etc. So you want to build these kinds of things to create these knowledge graphs. Now, in addition to reading text documents, what we do here, and I alluded earlier to the fact that our UCO system sort of subsumes sticks. So we also read all the publicly available threat feeds that you are getting from taxi servers. So for those of you who are familiar, Sticks threat feeds are essentially JSON representations of the same kind of information without the relationship spelled out. We can ingest them also and add them to our knowledge graph. And one of the first places we demonstrated this was using sort of Twitter. We built a system called CyberTwitter some years ago. So you might be saying, well, why do you need research? Isn't there like a bunch of people doing NLP, and can't you just download Stanford's NER? And well, this is the result if you download Stanford's NER. Right? It thinks there is an organization called Login Service. Obviously, that doesn't work because you really want to be able to do something like this, which is what we do. Right? So the entities that we look out for are described here. For some, you need sophisticated NERs. For other things like IP addresses, frankly, you can just build regular expressions and capture them. So what we are doing is sort of building a combination of, in this case, CRF-based, but we've also tried some deep learning methods more recently that have given better results to read that text, as well as regular expressions to pick up things like IP addresses and hash and so on and so forth in a piece of text. We annotated about 54,000 words from these various sources, trained and tested, and are getting pretty good results. So the harder part is to extract relationships. And relationships are hard because Anupam Joshi and UMBC are mentioned right next to each other. And looking at the words in between, you could maybe say, yeah, okay, Anupam Joshi works at UMBC. Anupam Joshi is mentioned in the first line of the document. UMBC is mentioned in the 5,000th line of the document. And yeah, in between, there are words that represent a works relationship. Should you be drawing that inference or not, right? So it's a harder problem, but we've built systems to extract, and I don't want to trivialize this, right? In general, that is an extremely hard problem. So we worked first on a more restricted version of the problem, which is to say, what security-related relationships, especially those captured in frameworks like Sticks and Attack, might exist between these two entities, right? So we're not asking we are only interested in whether something is a mitigation, something is an attack, something is a vulnerability, right? We're not interested in, oh, the cost of Microsoft Explorer is $5. We're just not interested in that relationship, so we don't even try to look for it. If you restrict the problem like this, you can actually build deep learning-based systems by essentially creating word embeddings representing the entities and training a deep network to say, given these two word embeddings, is there a relationship that explains them, right, or connects them? So we built this kind of a system and trained it using a large set of documents that our students annotated, and we are able to get fairly good results, right? So reading a text like this, we're able to pick up these kinds of relationships. Nikon targets spear phishing targets. It uses suspicious email. You don't see the relationship there, but there's a malware called Helsing that uses, has a particular hash, et cetera, right? So once again, you can look, the results are not as great as what you're getting for NER, but they're pretty reasonable. And in fact, in more recent work, we've kind of pushed these numbers up further. Before I move on to the final part of the talk, I do want to say something else, right? So I know we've been talking about how AI can be used to enhance cybersecurity. Well, every time you do that, if you think like a security analyst, you're saying, oh, you've just opened up another vulnerability. So what you've opened up now is data poisoning attacks. If I'm the adversary and I know you are doing this, I'm going to start putting fake documents on the net saying, hey, I found an attack on, Microsoft Word that does this. And I'm just going to read it and say, oh, new attack on Microsoft Word, and then begin to take defensive actions that might actually stymie my system, right? So there are sort of these challenges. I can also deliberately give you fake information. Right? I could say, oh, the way to mitigate this attack is by shutting down port 80 on your server instead of shutting down port 5034 or whatever it is. So in more recent work, and this is being written up for publication, so I didn't want to put any numbers up, but we are actually beginning to use some very interesting techniques to say, can I actually detect when someone is feeding me this kind of fake info? Can I detect these kinds of data poisonings that might be happening? But anyways, to continue, right? So again, these are actual texts we got from our friends at NSA after action reports. And you can see that this talks about, the Helsing thing and what kind of tools that it is using. So you can extract this information and create a knowledge graph. This is what the knowledge graph extracted from this particular document looks like. But again, they gave us 1.2 or 1.6, I forget, terabytes worth of information. So you're going to read a lot of documents. And there's probably going to be a lot of different after-action reports that are talking about the same malware, but perhaps adding new information every time. So it's not sufficient to say, oh, and then I write another one, and I created another knowledge graph, right? What you really want to be able to do is to say, hey, I ran a bunch of these reports, and these 100 of them are all talking about the same malware. So I will take the knowledge graphs I extracted from each one of them and fuse those knowledge graphs to create a single queryable source. And so this is the example of, this is the result of fusing those two knowledge graphs that I was showing you about. And now it has information from both those sources. So if an analyst is querying or a system is using it, you can do interesting things. So let me just end by giving you two simple things that were done by, well, at that time, people who were undergraduates. So this is about 2.5 years old right now. Lorenzo Neal, a Meyerhoff scholar who's now at North Carolina State doing his PhD. If there are any APL HR recruiters, he'll probably graduate in a year or so. You should think of hiring him, right? So Lorenzo was an undergraduate research assistant in my lab, and he took this tooling that our graduate students were developing and said, okay, every project in GitHub, and there's a lot of use of open source right now, has with it sort of this issue repository that says, what issues have been identified, including things like buffer overflows or, malformed inputs and things of that nature, right? So he used this to read all these repositories, construct knowledge graphs, and then he would go look at what. So you said, okay, I want to protect this system. So he would say, okay, what software do you have installed? Can I decompile and say, what libraries is it calling? Are any of these open source libraries? And if they are, let me go pull from my knowledge base all the known vulnerabilities that are afflicting those libraries. And I'll just tell the analyst, hey, boss, if you're running this version of this software, you may have these problems, right? And that itself is good knowledge. So this was an undergraduate working over the summer. Here is another undergraduate. She since went to a defense contractor, came back, is doing her PhD, and you can't hire her because she was just hired by NSA. So, Priyanka, we were discovering that when we were looking at the dark web, most of the discussion of interest around attacks, especially attacks that are relevant to us in the US, was not happening in English, right? Were often happening in Eastern European languages written in Cyrillic. So, okay, zeroth order idea, let's throw that through Google Translate and apply our English tooling. Except, if you throw that through Google Translate, and I have one good example, which is that if you look at, if you pass through Google Translate, this little thing that there was a report saying that there was a virus that was cleaned, Google Translate thinks that you are talking about like the real virus and the real thing you do to clean it with a bleach or something like that. So that's what Google Translate puts out. So obviously that doesn't work. So she had this interesting idea, and she worked with some of our graduate students to say, if you have tagged data in English and you have created a word embedding space, and for those of you who are not familiar, what you're essentially doing is creating a latent space that captures relationships between words. That's what word embeddings do. Very interesting technique developed around 2013 by Mikolov. So you have the latent space for English. Well, let me create directly by talking to a native Russian speaker. And we had another undergraduate who was a native Russian speaker. We said, well, why don't you translate a handful, a few tens of these sentences? And we said, okay, let me create the Russian embedding space about cybersecurity related data. And now I will find a mapping function because I know which documents here correspond to which documents there. I will find the mapping function in the embedded space. And so for any future documents, I will read them in Cyrillic, in Russian. I will map them directly. I will create the word embeddings in the Russian space. I will map them directly to the English space and then move it up through the translation thing. And then you get much better results, right? So again, this was another undergraduate. A little plug for UMBC, we are very good with undergraduates working in our labs, not just graduate students. So this was sort of another good example. What she's doing right now is fascinating, right? So she just published a paper late last year. So you can now actually use tools like this to create completely fictitious threat feeds. And we tested it by giving about 500 such documents to fairly senior security analysts working in the defense industry here. If a threat feed was true, they would correctly say, yeah, this is a real threat. For the threat feeds that we were generating, which were completely fake, they were like, their detection was 50% basically. So they were 50-50 on whether it was real or fake. So even fairly sophisticated analysts can be fooled by these kinds of tools that the NLP people, you may have heard about this. I mean, this is the same technology that is used by Google in the chatbots and all, right? How they generate these real sounding conversations and all, what are called large language models. So she used a well-known large language model, GPT-2, to generate fake tweets. I mean, a common example was she just gave it the first few words, the SolarWinds attack, and then it generated a completely real sort of sounding paragraph that had nothing to do with the real SolarWinds attack. It mentioned a completely different attack and a completely different way of getting in and so on and so forth. So, there's a lot of possibility here. So, yeah, these are some of the examples that I was talking to you about earlier. And that's my trophy. I thought I had a slide here that said questions, but let me stop here and see if there are any questions. Thank you very much. I appreciate your time today. And since I'm not on a computer, I can't see if anyone has
So I
posted
think
anything on the
Jeff
chat.
is going to look at the, so I think while folks on the web are trying to find out some questions, I have a question, Professor Joshi.
Yes, sir.
This is Ashutosh from Johns Hopkins, APL. So some of the technique that you mentioned, I work a lot on 5G security, which is more like network. Mm-hmm. So you have radio access network, edge cloud, you have SDN, virtualization, etc., right? And we're trying to find out how we can take advantage of AI to prevent the attacks. You know, not only reduce the time to detect and mitigate, but completely prevent.
Yeah. So I think that's a great question, and we can talk at greater length some time. But we are being challenged to do this on a big ARL project that we have, where we have to try and show the success of these kinds of techniques on, small form factor devices like Jetson Nanos, right? In fact, for a version we did to secure smart homes with a local startup through TEDCO funding, we were trying to run some of this on a Raspberry Pi. Because when you're doing this on the edge, your compute capability tends to be limited, right? ARL would like to fly little micro drones and have them think about, hey, my bandwidth availability certainly decreased. Should I switch from the 5G backhaul to the LoRaWAN and feed it, dump the data to the soldier and have that soldier push it out, right? So we're building these kinds of systems where we are trying to detect these attacks on the edge and mitigate them by, for example, transcoding kind of ideas, or switching the network channels, or doing a different frequency hop. So there are possibilities dealing with edge devices, and especially with ORAN coming on, and SDRs. There is great scope here.
Yeah, I have a question. Ryan Pepito, APL. I was just wondering, what do you feel the biggest challenge is with AI that is stumping you, and I guess reaching the goals you're trying to achieve within the work that you are doing?
Okay, that's actually a fascinating question that probably deserves like a 30-minute speech by itself, since I don't have 30 minutes. Don't want to keep you guys from dinner. In short, what I'll say is this, right? This kind of research is hard because you really need to understand the domain and the AI technologies involved. So you can't say, well, I'm the cybersecurity guy. All I know is that if you call scikit-learn or PyTorch and give it this deep learning model, you actually have to understand what is being done and why it's being done, right? So if I just walk in and without collaborating with Dr. Datta here, say, yeah, I'm going to do dwell time changes on the frequency hop, right? I may be completely breaking the system when I think I'm trying to defend. So I think that's a very big challenge, right? Getting the experts in AI and experts in some of these domains to talk together. And frankly, some of these AI challenges are generational challenges, right? So how humans think, how we reason, how we abuse, I mean, we have a foothold of it, but fundamentally, some of these are questions that you can go back and read papers in the 1930s about what it means to be intelligent. You can read papers from Searle in philosophy, right? On what does it mean to truly understand and know. So these are generational challenges. We're doing fairly straightforward stuff in terms of pushing the AI state. But if you say, what I really want to do is to augment the human analyst by creating something that almost looks like the analyst's natural intelligence, I don't have an answer. That's a big challenge. We're probably going to be spending, my career, your career, and perhaps the career of some other people after that before we can get to that.
Is it on now? All right.
Yep.
Hi, good evening. Eric Holst, APL, AMDS, Air4J. Thanks for coming to speak. I was just curious if there's anything kind of at the intersection between, what we're discussing here, which is more kind of like technical cyber attacks compared to social media or more kind of soft or psychological forms of, cyber engagement. If there's anything at the intersection of those two areas that you find interesting.
Yeah, so I guess let me start by saying the obvious, which is that a lot of people have been talking about misinformation or disinformation or whatever your favorite word is recently. We did some interesting work, how quickly time flies. Hurricane Sandy, right? I don't know if anyone here remembers Hurricane Sandy, but during Hurricane Sandy, people were actually, social media was beginning its sort of up inflection curve, right? So people were posting pictures on Facebook and whatnot and Twitter. Here is a shark swimming on the New Jersey Turnpike. Here is a McDonald's in Virginia Beach completely underwater. And what we were saying was, can we detect that these are fakes? And we had some good results. It was very topical, so got us some coverage in Wired and BBC and places like that, not just the normal journals where we publish this work. But I think the problem you are beginning to run into now is that your nation state adversaries are not necessarily confined to feeding a single piece of misinformation, right? What is more interesting is crafting of a narrative. Can I seed sequentially a little bit of misinformation, shades of truth, along with otherwise true information, to take your thinking along a certain direction, right? And we've seen this. I have zero clearances. I know some of you here may have clearances. You may know more than I. But one thing that was reported around the time of the 2016 election was this thing happened in Dallas, where there was social media activity that kind of was directed at the Muslim American population there, pointing out, some issues of potential mistreatment or how laws may be framed to exclude them and things of that nature. So getting people agitated a little bit and, suggesting that maybe there should be a demonstration to raise, these concerns at such and such place on such and such time. Around the time the community began to sort of pick that idea up, allegedly the same sources began to post in other groups, you can guess which ones, that said, look, these people come from other countries, and then they want to impose their views on us, and they don't want to adapt, and they're going to do a big demonstration here, and we should show up, and, a situation was created, right? So it's the same set of facts. I'm just mixing them slightly differently to take your thinking in a certain direction, right? I mean, I hate to be controversial, but the very unfortunate events that are happening in Ukraine right now, the Russian invasion, right? You can craft two stories with the same set of facts. In story one, an imperialist Russia, hell-bent on recreating its former Soviet empire, is trampling, right, the free rights of countries in its neighborhood to make whatever choices they want to associate with whoever they want. In narrative two, and you can see both of these not in the American media, but if you look media at the rest of the world, you're seeing both of these narratives, right? In the American media, you only see one narrative. The other narrative, which you don't see here very often, is America is creeping eastward after giving assurances, when the Soviet Union said, fine, we're giving up, let's just all be friends, etc. And they said, yeah, we will never, cause NATO to expand. And now slowly, one after the other, NATO is creeping next to our borders. What are we supposed to do? Same set of facts. Now you mix in a little bit of, information in different ways. So I think this is going to be an interesting, and we are interested in this problem, by the way. We're working with some linguists and all to identify how are narratives crafted. I mean, people in literature have studied this problem, right? How do you write a story? How do you expand the plot? But I think we have to get wise about this in the social media context, because a single piece of blatant disinformation is easy to detect, right? If someone posts and said, Professor Joshi gave a talk about, I don't know, quantum computing at APL today, it's pretty easy to figure out that that's wrong, right? But if someone says, Professor Joshi's talk was entirely about novel methods to do deep learning for entity detection, well, there's a kernel of truth in that. But that was, and you can just combine these kinds. So anyways, that's, for soft, that's the kind of thing that we're very interested in right now, talking to linguists and things of that nature.
Microphone. Yeah, so there was a question from the web, and my computer's about to shut down. Let's see if I can get it from my pad. Chat. Yeah. Here we go. So with the use of the Internet of Things at an industrial scale, it seems that this is encouraging adversaries to use fake IoTs. And so the question is, how can you use AI to isolate some of the adversarial IoTs?
Again, that's sort of a talk by itself. Let me give you an example of a specific piece of work we did that uses the same kind of technology. So I talked to you earlier about word embeddings really describing a latent space of relationships between words. So think about any real IoT or CPS system that operates in the physical world. It operates under certain physical constraints, right? So go back to Stuxnet. Those centrifuges are supposed to spin at a certain speed with very tight tolerances. If I remember, the tolerance is supposed to be 5%, right? And they should, even though a Siemens PLC is getting completely valid and validated commands saying that they should spin at 100% their normal rate, physics tells you that that is wrong, right? Now, of course, for a given system, you can query the experts and say, how do you come up, tell me the rules that the system should operate in. But realistically, with IoT, as you said, penetrating all aspects of our life, that's going to be hard. So what we said was, can we do the same class of techniques to see the latent space that is defined by the physics and the domain, right? So we took a car. One of my graduate students instrumented it, and IoT systems present an interesting example. I can't tell my graduate student, drive the car normally, and then to show an attack, drive the car at 100 miles an hour, or well, not 100, 65 miles an hour or 95, and open your door. Not allowed to do that, right? No IRB would let me do that, and I wouldn't do that. But what you can do is you can say, okay, let's drive the car under normal conditions, whatever physics says, whatever the real world usage says. And in this case, he drove the car for about 25, 30 hours in a variety of conditions. And you're gathering data from the OBD port essentially on a per second basis. So this is huge data. And then you build deep learning models to extract the latent space, to say, look, you may have, terabytes of data, but really there are only 5 or 6 real physical things. You're driving on a highway at normal speed, you're driving in rain, you're driving in snow, you're driving, in city streets, you're parked. There's 6, 7, 8, 10 things like that that represent normal. And I can, using deep learning techniques, identify normal. So if you now use some fake IoT systems or commands to try to push me out of that normal envelope, I can see whether my current state fits, is projectable into any of these underlying latent spaces. And if it's not, I will stop it. So that's one example, but again, there's lots of different ways of doing this. Thank you very much. Once again, I appreciate your calling me today.
Thank you, Professor Joshi, for that invigorating and exciting, interesting talk. We have a token of our appreciation that we will be presenting to you. I can read it today. It's not available today, but we'll be mailing this to you. But in appreciation for your talk, we will be presenting you with a plaque that reads as follows. The ACM Baltimore chapter extends its appreciation to Professor Anupam Joshi for delivering an invited talk, ACM Baltimore chapter inaugural seminar 2022, Laurel, Maryland, April 20, 2022. Thank you very much.